Hello everyone, so today we're going to discuss dot products. I think this is a really interesting topic. It's not the most difficult, but it's generally one that people tend to get confused on. Well, okay, so we have two vectors, u here and v. They have an angle theta between them, which is denoted here, and we define the dot product as u dot v here equals to the magnitude of u times the magnitude of v times cosine of theta. So what is it physically? Well, we can say that if we project u onto v, as denoted by this line, so this is the projection denoted here, u cosine of theta. So what's the projection? Well, a projection is essentially the component of u in the direction of v. So it's this. So it's the component of u in the direction of v. Right? So this is u cos theta, and then we multiply by the length of v. And that's the definition of a cross product, of a dot product, sorry. So again, you project u onto v and then you multiply by the length of v. Well, an immediate consequence of this definition is that u dot v must be equal to v dot u. And this can be seen from this figure, where we have the same two vectors v and the vector u here, and we project v onto u, and we have v cosine of theta, and then we multiply by the length of u, which gives us u v cos theta. So we have the definition in the bag and we understand dot products. So immediately we can say that there are two properties from this definition. U dot v equals 0 if u is perpendicular to v. Well, why is that? That's because cosine of theta is, when theta is 90 degrees, is 0. And I've drawn it on the graph here. And then we have u dot v equals magnitude of u times magnitude of v if u is parallel to v. That is, if u is parallel to v, the dot product is a simple product, right? And I should say parallel in the same direction, so I'll denote it by this. This is not really formal, but here we go. Because if it's opposite directions, then it would be u dot v is minus, because then we would be at theta is 180 degrees. Right, so this is minus 1. This is 1. Okay, so now let's define the coordinates. So we have a regular run-of-the-mill, I shall call it, coordinate axes with ex, ey, and ez. So here, yeah, ex, ey, and ez. And using the definition of a dot product, it's pretty easy to show that ei dotted with ej, where I and j represent x, y, or z, equals 0 when I is not equal to j. So for example, ex. Oops, what happened? Sorry about this. This is a new platform. Let me just erase this and let me start again. So ex dotted with ey, for example, equals 0. But ex, let me erase this, ex dotted with ex equals 1. Right, so that's pretty easy. So now, this gives us a way to essentially take out components. But some of you will have encountered this, and you say, well, what is this definition, right? Because we define the dot product very differently in our regular math classes. Well, this is often called the geometric definition. And let's get on to the algebraic definition, which is given as follows. Well, we can say u dotted with v is ux, ex plus uy ey plus uz ez dotted with v, which is vx ex plus vy ey plus vz ez. And distributing the dot product over the brackets, we get ux vx ex, which comes from this term, these two terms, right, to get that term. And if you carry on, you get ux times vy to get this term, ux vy ex dotted with ey, and you can carry on doing this for each of the terms, and then using the rules which we've just seen. So ex dotted ex equals 1, and ex dotted ey will be 0, etc. So when we can cross out these terms, and then it's quite easy to realize that we get back our expression ux vx plus uy vy plus uz vz, and this is often called the definition of the dot product. But clearly it can be derived using the the geometric definition. Well, some of you have realized that, hang on a minute, we've assumed that the dot product is linear, and we don't know beforehand that our definition of a dot product as a projection agrees with linearity. So we don't know whether the process shown in the first picture, sorry, I'm scrolling back, in the first picture here, where we project u onto v and then multiply by the length of v, whether this process is linear. And by linear, I mean, let's scroll back, we need to prove that u plus v dotted with w is the same as u dot w plus v dot w. If we can prove this, right, then we are allowed to distribute the dot product over the brackets as we've done here. So, what's the geometric proof? Well, we have two vectors, u and v. U is drawn in blue, v is drawn in red, so there we go. And the black lines, which is that line and that line here, are the projection of u and v onto vector w. So here we have the projection of u, and here we have the projection of v. So this is v's projection, and this one is u's projection. Right, and then we need to prove that the projection of u plus v, which is shown in this red sort of fancy font, the projection of u plus v must be the same. But clearly from the diagram, we can see that if we project u plus v onto w, then what do we get? Well, we get this right here, right, which is exactly the same as the sum of the projections. So that's exactly what I wrote on the side. Clearly, projection of u plus v onto w is same as sum of projections of u and v onto w. Therefore, we've proved it. And yeah, there we go. This is the way I like to teach the dot products. Okay, and now we can see the law of cosines very quickly as an extension of dot products. But this is a direct consequence of geometric definition of dot product. So if we have two vectors, let's say b, a vector a, and a vector c, then we know that A plus C is equal to B, right? And now we can take the dot products to prove cosine law, and I'll leave that as exercise. And you should tune in to my next video where I'll just take up from here. Thank you and see you next time.